Hello everyone, welcome to the Lab 5 of Advanced Embedded Logic Design Winter 2022 semester. In the previous videos, we discussed about the introduction of the interrupts, and we also discussed what are the changes we need to do in the hardware block design to enable the interrupts. Now we are going to discuss about the interrupt handling in the zynq SoC. So in the zynq SoC, we have the Cortex A9 processor. And in the Cortex A9 processor, we have the GIC, that is the Generic Interrupt Controller. And this GIC will handle all the interrupt. Now, the programming of the GIC or the handling of the GIC is done via the interrupt handler, which is supplied from the Xilinx. So in this lab, we need to understand how to configure this interrupt handler and how to connect this interrupt handler to the ISR of the interrupt so that we can process the particular interrupt. So in the Cortex A9, we have the interrupt handler mechanism inside the each core. We have the GIC, General Interrupt Controller, and then we have the different interrupt sources. So we need to create instance of the GIC similar to that we did for the DMA, and we need to initialize the board. And how we do? We create a structure, one for the GIC instance and one for the GIC configuration data. This is same as what we did in the previous lab for the DMA. So for any IP we add, we need to include the corresponding .h file. We need to create the instance structure and we need to create the configuration structure. Then using the ID of that corresponding unit, like for example, GIC, we will copy all the configuration data, which is usually there in the xparameter.h file in our local configuration structure. And using this local configuration structure, we will create an instance of the GIC in our application code so that we can configure the GIC as per our requirement. So why this is needed? So in the interrupt, you can see that when the interrupt happens, we need to identify the source of the interrupt. So because there are so many sources, we need to identify source of the interrupt. Then we need to also decide whether the interrupt to be processed or not. So we need to decide whether it's a maskable or not. Then if the multiple interrupt receives at a time, then we need to decide which to be processed. So we need to decide the priority. And then the fourth, we need to have the particular ISR, interrupt service routine, to be executed. So all these tasks, we need to have someone who complete this task, and this is nothing but the GIC. So the Cortex A9, when it gets the information that there is one or more interrupts are there, then the Cortex A9 core will communicate with the GIC to know which interrupt to be processed, how it should be processed, what is the priority, and so on. So the Cortex A9 will depend upon the GIC to get all the information about the interrupt. And that's why we need to create an instance of the GIC in our application code. So the ARM CPU cores have the internal exception handling logic. Okay, that means whenever the interrupt happens, what are the things to be taken care to process that interrupt is handled by this interrupt exception handling logic. In some of the processor, it is disabled and uninitialized at the power up. In case of the Cortex A9, it is already enabled and the initialized. Also, there is one standard interrupt pin, IRQ. Similarly, there will be FIQ, but here we are focusing on the IRQ pin on the Cortex A9 core. And there is a master interrupt handler So this is nothing but a vector table, okay, which will tell the core to communicate with which GIC. So here we have this GIC. Tomorrow you may write your own GIC. So in that case, we will tell this master interrupt handler that you should communicate with that particular GIC. So there is a master interrupt handler which the CPU executes when receiving any interrupt request. This handler is unassigned because this handler should know to whom to contact with when the interrupt happens. Okay, this is also unassigned. So we need to make sure that we take care of the assignment. Inside the GIC, that is a general interrupt controller, it has the ability to manage the many interrupt inputs and has a table which allows the interrupt handlers to be assigned. Interrupt handler nothing but the ISR to be assigned when the interrupt happens. So everything is unassigned. So you need to make sure that whatever the interrupt sources are there, for that you give the address of your ISR. Then each interrupt input on the GIC. So each interrupt input on the GIC, these are also the inputs, has enable switch that is disabled by default. So you can see that there will be some control register inside the GIC. You need to make sure that you write appropriate value in the control register so that the particular interrupt is enabled at that particular time. So for example, for certain time you need to disable the particular interrupt. You can disable it via writing into the control register. So when you enable that corresponding switch, that means you are writing into the control register. Similarly, for every peripheral or the source of the interrupt has an output enable switch that is disabled by default. So by what you do the write operation on the control register of the interrupt source, and then you inform that device that now you can generate the interrupt. Okay, that is what you do in this step. So in the simple meaning, you are closing those switches. Okay, now to revise the steps which we need to do for this process. First, we need to initialize the exception handling logic inside the ARM processor. Second, we need to make sure that the master interrupt handler in the core is assigned with the appropriate GIC so that the core knows to whom to contact when the interrupt request comes. GIC has the ability to manage multiple interrupts input, and we need to make sure that we connect our ISR to the appropriate location inside the GIC. We need to make sure that we close all the switch or we enable the interrupts at the GIC input as well as at the peripheral output. Okay. So the last discussion we had about this process can be mapped to the 6-step process, and then we need to write the ISR for every interrupt source. So the first step is this, that we need to initialize the exception handling unit in the ARM processor. As I told you, it is not initialized in some of the processor. In Cortex A9, it is already initialized. So you will see that this function is an empty function. Okay, so you can skip this step. Then the second step is that you need to make sure that when the interrupt happens, the processor has to integrate the GIC to find out which peripheral has generated the input. So we need to connect the link between the processor and the GIC. For that, we use this exception register handler, okay, where this is the Xilinx supplied register handler, and we are telling this that you should contact this INTC instance pointer. This is nothing but our GIC pointer, which we have initialized in our code. We need to connect this. Then third step, Xilinx provide the interrupt handler to do this automatically, and this is nothing but the corresponding interrupt handler. Now we need to make sure that for every source of the interrupt, we write the ISR in that one. So interrupt specific handler has to be assigned to the peripheral. Interrupt specific handler is nothing but the ISR. So it is connected to the unique interrupt ID. So every interrupt will have the unique ID. list of these IDs are there either in the X parameter ps.h if the interrupt source is in the PS, or X parameter.h if the interrupt source is PR. So here, this is a very important thing. The previous two steps are independent of the number of sources, interrupt sources, but this step should be repeated for every interrupt sources. In our case, we have the two interrupts. One is from the MM to S interrupt, second is S to MM interrupt. So we'll repeat this process. So you can see that this is my GIC instance. This is the interrupt ID for MM to S. This is there in the X parameter.h file. Okay. Then this is the, you can see that my ISR, this function we need to write it. And this is nothing but the source of the interrupt. In our case, it's a DMA. This is used as a callback reference when we call the ISR, which we'll discuss it at the after few slides. Similarly, you need to repeat this for the S to MM. Again, the same instance pointer. This is the separate ID. It is there in the X parameter.h file. This is the separate, you can write a separate ISR for every interrupt, or you can use the same ISR depending upon your functionality. And this is the source of the interrupt. So with this step, now the GIC knows what should be done when the interrupt comes from this particular interrupt source. Then we need to enable the interrupts at the GIC. So the corresponding GIC enable function is there. And we need to enable the interrupt at the interrupt source. In case of the DMA, we have the corresponding DMA interrupt is there. So you can see that in case of the GIC, to enable the interrupt from MM to S, this is the ID which is there in the X parameter.h file. On the other hand, in case of the DMA, they identify the interrupt based upon the direction here. So you need to take care that you configure these things appropriately. Another important thing is that in case of the AXI DMA, it can generate interrupt in three cases. One is then when the transfer is complete, then it generates the interrupt. Second, it generates the interrupt when there is an error. And third, it's generate the interrupt because of some delay. This is used in the scatter gathered mode, which we'll discuss it later. So we have the option to enable the only one interrupt or only two interrupts or all the interrupts. So corresponding masks are given in the .h file. So usually if you see in the C code, you will see that there is a one particular bit for this interrupt, then another bit for this interrupt, another bit for this interrupt. And if you want to enable all the interrupts, you need to make all the three bits one. So this mask value, you will see that it is 7. It is enabling all the three interrupt. And when you interrupt enable, as I told you before, we are writing into the control register. And when we write this value, we are telling the DMA that you are allowed to generate all the three types of interrupt. Okay. And the last step is to enable this exception logic. So that's, we are telling the ARM processor that we have set up the interrupt, we have provided all the information. Now you should be ready to accept the interrupt. Okay. So these are the steps we need to follow while configuring the interrupt. Okay. So the important part of after these steps, after this 6 step, the next important step is the ISR, which is the writing the ISR routing. So before we go to the ISR routing, I'll just show you the corresponding C code explaining the how to set up the interrupt. So in our C code, we have already shared the dummy C code with you. In that C code, we are going to write a separate function for setting up the interrupt. Again, if you want to know more details about this, Xilinx has already provided the reference code, okay, reference code for how to set up the interrupt in DMA. So you can search it online, you will get the corresponding reference code. But that code, it will take some time to understand. So I have simplified that code for our lab purpose. So in our setup interrupt function, you can see that we are first configuring the GIC. Then we are doing the step 1, which is initializing the exception handling in the ARM processor. Then we are connecting the GIC with the core 0. Then we are connecting the 2 interrupt sources inside the GIC. And then we are closing the switches on the GIC. Then we are closing the switches on the interrupt sources. This is the optional step where we are setting up the priority of the interrupt. This is the optional, you can skip it. Okay. And when your application is complete, you can disconnect the interrupt, and for that you can use this code as well. But again, this is also optional step. Okay. So now the next important thing is how to write the ISR. So ISR is an important part of the interrupts in the embedded system, and we need to make sure that we follow certain guidelines while writing the ISR. As we know that the ISR is the function that will be called by the GIC when the corresponding interrupt happens. Okay. So whenever the corresponding interrupt happens, GIC will look for the interrupt source, and based upon the interrupt source, your GIC will call the ISR. You may write a separate ISR for every interrupt source, or you can write the same ISR for the multiple interrupt sources. It depends upon what the things you need to do when the interrupt happens. Whenever you write the ISR, the first thing you need to make sure that you are executing the ISR for the correct interrupt source. So you need to make sure that you verify the source of the interrupt inside the ISR. So that's what this callback reference which we discussed is useful. It will give us the information about who has generated the particular interrupt for which this ISR has been called. Keep the ISR code as short as possible, as simple as possible, because the interrupts will be generated only in response to the specific event. So it is very difficult to get those conditions or replicate those conditions while debugging. Also, whenever interrupt happens, the processor is executing the ISR. That means you are making the processor, you are asking the processor to branch from the normal program flow and to execute the ISR. That means your normal program flow is getting affected. So we want the processor to come back to the normal program flow as fast as possible. So keep in mind that interrupt keeps the processor away from the main function, and hence processor should spend as less time as possible in the ISR. So instead of executing a very complex task in the ISR, what you should do is that you should generate some flag, which those flags you can check in your main code, and you can take the appropriate action based upon those flags. So don't execute the complex task in the ISR. You can disable all the interrupts while serving. So suppose you are executing the ISR and another interrupt happens. Then what will happen? You will jump to the next ISR. So instead, to avoid such jumping, what you should do, whenever you go inside the ISR, you should disable the interrupts, then service the ISR, but make sure that you clear the interrupts as well as enable the interrupts before leaving the ISR. So enabling is important to generate the next set of interrupt. And if you don't clear the interrupt, then the IP will assume that my interrupt has not been processed, and it will regenerate the interrupt. So that's why it is very important to clear the interrupt or to acknowledge the interrupt when the ISR is executed. Okay, so these are the things you should follow carefully while writing the ISR. So in case of the zynq SoC, Xilinx have included some code in their driver using the callback reference to identify the interrupt source. The Xilinx interrupt handler XSCU GIC interrupt handler calls the ISR, and it also passes the information about the driver instance which is relevant to the peripheral that generated the interrupt via callback reference. So by using this callback reference facility, you will know the source of the interrupt inside the ISR. And how this is done, in our SCU connect function, what we do, we tell the GIC that when this interrupt happens from this source, you should execute this function ISR, and to this ISR you should pass this information. This is the information about the source of the interrupt, and this is nothing but the structure which has all the information about the DMA. Okay, like its base address and everything is given inside this structure. So I'll explain you some example of the ISR which we can use it in our DMA example. So you can see that this is my callback reference. Using this callback reference, I'll know everything information about the source of the interrupt. So now here I'll know the base address of the DMA, and using the base address of the DMA, I'll get the status of the corresponding interrupt. So here what I'm doing, I'm asking my DMA to send the status of the interrupt in this direction. So what I'm doing at the end, I'm doing the status register ready. So as I told you, DMA can generate 3 types of interrupt, and based upon that you will get this 32-bit register. And then now what you are doing, you are acknowledging the register. That means you are telling the DMA that now I have accepted your DMA interrupt request. I'm going to process it. So you should clear that corresponding flag and you can accept the new set of interrupt. That's what I'm doing it here. So I have completed the reading the status of the interrupt and the clearing those interrupt. Now I know that the interrupt has, there is a interrupt request, and I know that this is the status of the interrupt in the IP. First, I'll check whether anyone has generated the interrupt, whether that DMA has generated the interrupt. Okay, so I'll check whether the corresponding bits in the register has been set or not. So I'll check it corresponding 3 bits are set or not. If none of the bits are set, that means I had received the interrupt, but this was not received. This was not corresponding to the appropriate source. So I'll ignore that interrupt. Then what I'll do, if this is not true, then that means the interrupt was generated. So I'll check for the 2 conditions. One is the error condition, and the second is the transfer successful condition. Okay. If the transfer is successful, what I'm going to do, I'm going to make the corresponding flag is equal to 1. This flag I'm going to check it in my main code. If there is an error in the transfer, so you can see that there is an error bit has been set, then in that case what I'll do, I'll make the error flag is 1, so that in my main code I know that the error has happened. Then I also make sure that I reset the DMA. This is also important because DMA has gone into the error, so it is good to reset the DMA. And sometimes what happens that the reset doesn't happen in one go, so I'll wait for certain time to make that reset to happen. Again, this part is completely optional. You can ignore it. You don't want to spend time on this one. Okay, so this is the important of the ISR. Now the question is why you need to send the callback reference. Why you want to send this one? Note that this function, the AXI DMA structure was defined in our some other function, and it is local to that function. So this information is not available to the ISR. So that's why we need to send this callback. This is the important facility. So original AXI DMA ACP structure is not within the scope of ISR. So by using the local copy instance, we know that we can get the information about the DMA, and we'll be able to read and write the control and the status register of the DMA. So this is exactly copy of the one in the main function, and you can modify the DMA. So any changes to that local copy will also apply to the original copy because they are linked together using the pointer. Okay. So with this, let's quickly revise our code. So I'm going to write this function in my FFTPS ACP interrupt function. After I do the DMA configuration, before I start my FFT experiment, I'm going to set up the interrupt. I'm going to pass the instance of the GIC, instance of the DMA, and the 2 sources of the interrupt. Their IDs are there in the xparameter.h file. Then in the same code, before I start the experiment, I'll initialize the flags to 0, and then I'll start my experiment. Then after I do the simple transfer, I'll wait for one of the flags to become 1, and based upon that, I'll display the error. Okay. Then at the end, I'll do the disconnect after my for loop is completed. So these are the steps we need to do in our this function. Okay. So I hope this will helpful for you to complete the rest of the